The next industrial revolution will be invisible to the human eye. Microscopic machines are preparing to unlock the solar system's vast riches, turning asteroids into the mines of tomorrow. By the end of this, you will understand how this fusion of nanotechnology and space mining will reshape our world. How can tools smaller than a blood cell build an entire industry in the vacuum of space? And what happens to our economy when cosmic resources become limitless? What does a future of true abundance really look like to you? That single asteroid, laden with platinum, represents more than just wealth. It is a promise of a future unconstrained by the limits of our own planet. The rare earth elements locked within these rocks are the very same ones that power our smartphones, our electric vehicles, and our advanced medical equipment. Their scarcity on Earth creates geopolitical tensions and environmental devastation, with entire landscapes torn open to recover mere traces of material. But out in the void, these elements exist in almost incomprehensible abundance. Water ice, frozen in the shadows of asteroids, is not merely for drinking. When split into hydrogen and oxygen, it becomes rocket fuel, effectively turning these space rocks into cosmic gas stations for deeper exploration. The challenge, however, is as vast as the reward. How do you set up a mine where there is no ground to stand on, where gravity is barely a suggestion, and where traditional heavy machinery would be useless, floating away with every operation? The brute force methods we use on Earth simply will not work in space. The solution demands a complete rethinking of industry, moving away from massive drills and smelters and towards something far more elegant and precise. We must build not with bulldozers, but with billions of microscopic agents. The sheer impossibility of building a traditional mine in zero gravity points toward a radically different solution. To grasp the engine of this revolution, you must first shrink your perspective down to the nanoscale. This is the realm where measurements are counted in nanometers. 1 nanometer is 1/1000th of a meter, a size so small it defies everyday comparison. Picture the width of a single human hair. Now imagine splitting that width into 80,000 slices. One of those slices is roughly 1 nanometer. At this incredible scale, the world does not operate as we expect. The classic laws of physics that govern our daily lives begin to soften, and the strange, probabilistic rules of quantum mechanics emerge. This shift is not merely a scientific curiosity. It is a gateway to new material properties. A simple piece of carbon, when arranged at the nanoscale, can transform into graphene, a substance hundreds of times stronger than steel, yet incredibly flexible. Common metals like platinum can become vastly more efficient catalysts, speeding up chemical reactions that would be sluggish or impossible with larger chunks of material. This is the core of the revolution. It is not just about miniaturizing our existing tools. It is about harnessing an entirely new library of material behaviors that only exist at this infinitesimal level. By learning to build and control machines at the scale of molecules, we gain the ability to perform industrial tasks with a level of precision and efficiency that is simply unattainable with hulking machinery. This foundational leap in capability is what makes nanotechnology the perfect key for unlocking the riches of the solar system, setting the stage for an industry that operates with the quiet hum of billions of microscopic workers. This seed factory concept transforms the entire economics of space. Picture a single spacecraft, not much larger than a car, journeying to a distant asteroid. It carries no smelting furnaces or conveyor belts. Instead, its cargo bay opens to release what looks like a shimmering, intelligent dust. Each speck of this dust is a nano-assembler, a microscopic machine equipped with its own simple intelligence and a fundamental drive to build. Their first and most crucial task is to build more of themselves. This is the principle of self-replication, a process that turns a small initial investment into an astronomical workforce almost overnight. It is the ultimate bootstrap operation, using the only available materials, the asteroid itself. These nanoscale workers would descend upon the asteroid's surface, a barren landscape of rock and metal known as regolith. They do not mine in the traditional sense, they disassemble. Using precise chemical or mechanical processes, they break the regolith apart, sorting its chaos into a pure, organized stream of individual atoms. Iron, nickel, cobalt, silicon, and even oxygen atoms are carefully separated and catalogued. This atomic stockpile then feeds a microscopic assembly line. Guided by their programming, the assemblers begin stitching these atoms back together, not into random rock, but into perfect, functional copies of themselves. One becomes two, two become four, then 8, then 1,000,000. In a surprisingly short time, that initial cloud of dust has become a trillion-strong swarm, a dedicated workforce born entirely from the resources of their new home. But their purpose extends far beyond mere replication. This growing army of assemblers has a greater mission. They begin constructing the larger infrastructure needed for a permanent operation. From the same atomic soup, they fabricate vast, ultra-thin solar panels to capture energy from the distant sun. They assemble communication antennas to maintain a link with Earth. They even build the girders and frames for a future processing station, all atom by precise atom. This approach, called in-situ resource utilization, completely overturns the old space model. We are no longer forced to launch every single nut, bolt, and solar panel from Earth at an astronomical cost. Instead, we send the blueprint, the tiny seed of a factory that can grow into whatever we need, using the unlimited and free materials waiting in the void. The dream of a truly self-sustaining industry, one that can expand across the solar system without constant resupply from home, hinges entirely on this beautiful, efficient loop of self-replication. This surgical precision is where nanotechnology truly outshines our past efforts. Think about a traditional mine on Earth, a place of immense noise and power. Enormous trucks haul countless tons of raw ore. That ore is then crushed into a fine powder and doused in powerful, often toxic, chemicals to leach out a tiny percentage of valuable metal. Over 99% of the material handled is ultimately discarded as waste, a monumental effort for a minuscule return. This brute force process is not just inefficient, it is environmentally devastating on a planetary scale. But in the silent void of space, a different kind of operation is taking shape. Instead of massive machinery, think of trillions of molecular sorting machines, each one a specialized worker smaller than a wavelength of light. These are not crude tools, they are more like programmable, intelligent tweezers operating at the atomic scale. Their mission is one of pure selection. A swarm of these nanoscale devices could be dispatched across an asteroid's surface with a single command: find the platinum. They would ignore the common iron and nickel, pass right by the silicates and rock, their molecular sensors tuned to identify and latch onto only the specific atomic signature of platinum group metals. With gentle, precise movements, they would pluck these precious atoms directly from the surrounding matrix, one by one. This changes everything about resource extraction. There is no crushing, no grinding, no smelting in giant furnaces that demand colossal amounts of energy. The purity begins at 100% from the very first moment of collection. As these microscopic workers harvest their designated atoms, they would ferry them to centralized collection pods, slowly filling them with a stream of perfectly pure, ready-to-use material. The messy, dangerous, and wasteful intermediary steps that define mining on Earth are completely eliminated. The processing footprint shrinks to almost nothing, and the concept of a hazardous byproduct simply ceases to exist. This is not merely an improvement on an old method. It is the birth of an entirely new paradigm for industry, one built on absolute efficiency and minimal environmental intrusion, even on an alien landscape. Once you have a swarm of assemblers harvesting pure metals from the surface, the next logical step is to look deeper. Asteroids are far more than simple lumps of ore. They are complex geological bodies, often resembling a pile of rubble loosely held together by their own meager gravity, with compositions that can vary wildly from their crust to their core. Sending in a conventional, heavy drill would be a recipe for disaster. The vibrations and force could easily shatter the asteroid's fragile structure, sending valuable material spinning off into space or causing the entire body to break apart. The brute force that works on Earth becomes a destructive liability in the zero-gravity environment of space. The answer is not to push harder, but to be infinitely more clever. This is where nano-enhanced drilling and tunneling mechanisms come into play. Instead of a massive, rotating drill bit, envision a tool that looks more like a delicate probe. Its tip is not made of common tungsten carbide, but is coated in a seamless layer of carbon nanotubes. These tubes, each one just a single atom thick and rolled into a cylinder, form a material hundreds of times stronger than steel and incredibly resistant to wear. Or imagine the tip being fashioned from diamondoids, synthetic diamond-like structures assembled atom by atom, making it virtually impervious to abrasion. But the real magic is not just in the hardness of the tool, it is in its method. This is not drilling in the traditional sense of grinding and crushing. This is a process of molecular persuasion. The nano-engineered tip would interact directly with the atomic lattice of the rock. It could use precise vibrations, targeted chemical reactions, or subtle electronic fields to encourage the atomic bonds in its path to simply release. It would systematically unzip the rock structure, persuading it to disassemble itself one molecular layer at a time. The result is a clean, stable tunnel carved with surgical precision, with no violent vibrations and no risk of fracturing the asteroid. This gentle power opens up incredible possibilities. We are no longer limited to scraping the surface. We can now bore deep into the heart of the asteroid, creating vast protected chambers inside the rock itself. These spaces could serve as perfectly shielded storage for the harvested materials, safe from the radiation and micrometeorites of open space. They could even become the foundational structures for long-term human habitation, with the asteroid's own bulk providing a natural barrier against the hazards of the cosmos. This approach fundamentally redefines the asteroid's role. It is no longer just a resource to be consumed, but a piece of raw cosmic infrastructure, waiting to be sculpted from the inside out by the quiet, patient hands of nanotechnology. The true power of this microscopic revolution lies not just in extraction, but in sight. Before a single assembler begins its work, we need to see the invisible. An asteroid is a dark, unknown world, and traditional prospecting is hopelessly blind. Sending a single robotic lander to drill 1 or 2 core samples would be like trying to understand an entire forest by examining 2 leaves from a single tree. The composition of these space rocks can shift dramatically over just a few meters, with pockets of extreme wealth hidden within vast fields of common stone. Guessing where to start based on such limited information would be a colossal and expensive gamble. The solution is to give the asteroid itself a voice. This is the role of smart dust, the ultimate prospecting tool. Picture a capsule opening high above the asteroid's surface, releasing a cloud of what looks like glitter. Each speck is a self-contained mote, a wireless sensor no larger than a grain of sand, but within its tiny body, it carries a sophisticated laboratory. Nano-engineered components allow it to detect the unique atomic signature of the elements around it, measuring local concentrations of platinum, gold, or rare earth metals. It can sense the density of the rock, track minute temperature fluctuations, and even feel the subtle structural stresses deep within the asteroid's body. These thousands of individual motes do not operate alone. As they settle onto the surface, embedding themselves in the regolith, they begin to talk to one another. They form a vast, distributed network, a living nervous system that spreads across the entire celestial body. Each mote shares its local data with its neighbors, which relay the information onward, building a collective intelligence. Piece by piece, they assemble a dynamic, three-dimensional map of the asteroid's interior, revealing the precise location, size, and purity of every resource vein. For the engineers back on Earth, this changes everything. Instead of staring at a vague, gray rock through a telescope, they would have a real-time data stream painting a vivid, high-resolution picture of their target. They could watch as the smart dust network highlights a rich plume of platinum group metals snaking through the asteroid's core, or identifies a stable, dense region perfect for tunneling operations. This is the difference between digging a random hole in your backyard and having a full architectural blueprint that shows you exactly where the treasure chest is buried. With this unprecedented clarity, the entire mining operation can be planned with surgical precision from day one, ensuring that the first cut is also the most profitable, turning a cosmic gamble into a calculated, sure bet. The final piece of this puzzle is the collective intelligence of the swarm itself. While a single nanoscale worker is a marvel of precision, its true potential is only unlocked in a vast, coordinated colony. This is not a top-down army commanded by a single leader, but a fluid, adaptive superorganism behaving much like a colony of ants or a hive of bees. Each individual unit possesses simple programming, but together they create a powerful, emergent intelligence. Within this swarm, specialization is key. Certain nanobots would be designed as excavators, their molecular tools fine-tuned for breaking specific atomic bonds in the rock. Others would act as transporters, forming efficient chains to ferry raw materials to collection points. A third group would function as builders, using those same materials to assemble new structures or even repair other members of the swarm. They communicate not with complex radio signals, but through simple, localized networks, perhaps using chemical markers or short-range vibrations, creating a constant, humming conversation across the asteroid's surface. This distributed system grants the swarm an incredible resilience. If a team of excavator bots encounters a vein of material that is too dense or difficult to break down, they do not simply keep pounding away. They signal the obstacle, and the swarm's collective intelligence instantly recalculates. It might redirect the excavators to a softer, more profitable area nearby, ensuring no effort is wasted. Should a dangerous solar flare erupt from the sun, bathing the asteroid in radiation, the entire workforce could receive the alert and simultaneously disperse, retreating into the safety of small tunnels or the shadowed sides of boulders, waiting out the storm. This adaptability makes them the perfect labor force for the profound unpredictability of space. They form a workforce that never sleeps, never requires oxygen or food, and can be reconfigured in real time for any task. The result is a mining operation that feels less like industrial machinery and more like a living, thinking entity, capable of reshaping an entire world with a quiet, fluid grace that larger, clunkier robots could never achieve. The harvested materials from these microscopic miners are destined for a grander purpose than a simple journey home. The real transformation begins when we use these cosmic resources to build a permanent human presence in the void. This is where nanomaterials truly become the architects of our future. The platinum, nickel, and iron collected from an asteroid will be fed directly into space-based nanofactories. These facilities, perhaps run by advanced versions of the same assembler swarms, could weave carbon atoms into flawless carbon nanotubes. These tubes, each one a perfect cylinder of carbon just 1 atom thick, possess a strength-to-weight ratio that defies belief. Picture a spacecraft hull woven from this material. It would be feathered light, yet many times stronger than the thickest titanium alloy used today. Such a vessel could withstand the impacts of micrometeorites that would shred conventional hulls, and it could carry humanity to the distant moons of Jupiter and Saturn on journeys that are currently the stuff of dreams. This leap in material science is not just about stronger ships, it is about building new worlds from scratch. The same nanoassemblers could fabricate vast, intricate structures in the vacuum of space. They could construct orbital space stations with the spaciousness of cities, or surface habitats on the Moon and Mars that feel less like bunkers and more like homes. Envision a dome on the Martian surface, not made of opaque metal, but from a transparent aluminum nanoceramic. This material, assembled atom by atom, would offer the incredible strength needed to hold back the thin Martian atmosphere, while providing radiation shielding superior to meters of concrete. And through its crystalline clarity, colonists could watch the sun rise over the red plains, with natural light bathing their interior gardens. This vision shatters the old economic model of space exploration. We are no longer trapped by the tyrannical cost of launching every single gram of material from the bottom of Earth's deep gravity well. By learning to build what we need from the resources that are already in space, we create a self-perpetuating cycle of growth. The nanotechnology unlocks the asteroid's riches, and those very riches are then used to build more advanced and powerful nanotechnology right there, in the high frontier. The mine builds the factory, and the factory builds the future. This elegant separation reveals a deeper truth about the entire endeavor. The absence of gravity, long seen as the primary obstacle to industry in space, is not a barrier at all. It is the very condition that makes such pristine manufacturing possible. On Earth, gravity is a constant, brutal force that complicates everything. It causes heavy particles to settle out of mixtures, forcing us to use energy-intensive centrifuges or complex filtration systems to achieve any kind of purity. In the persistent pull of our planet, achieving a perfectly uniform mixture or a perfectly clean separation is a constant battle, but in the quiet of space, that fight simply vanishes. Without gravity's heavy hand, every particle in a solution floats freely, creating a perfectly mixed environment by default. This allows nanotechnology to perform its work on a level playing field, where the only forces at play are the ones we intentionally engineer. The challenge shifts from fighting gravity to harnessing more refined tools. Magnetic nanoparticles exemplify this new approach. Imagine introducing a cloud of these tiny particles into a slurry of pulverized asteroid material. Each nanoparticle is engineered with a specific molecular lock on its surface, a key that only fits the atomic structure of, say, platinum. As they drift through the mixture, they selectively latch onto the precious platinum atoms, ignoring the common iron and nickel. Then, with a simple activation of a magnetic field, the entire tagged collection is gently drawn out of the mixture. The non-magnetic waste material is left behind, and the platinum is collected with 100% efficiency. This is a separation process of stunning elegance, one that simply cannot be replicated under terrestrial conditions where gravity would constantly interfere. The same principle applies to gases and liquids. Nanofilters with pores engineered to atomic precision can separate molecules not by weight but by their size and shape. In microgravity, these molecules drift and collide in a perfectly random dance, a process called diffusion. This natural motion brings them into constant contact with the filter membrane. Only the molecules small enough to fit through the pores will pass, creating streams of ultra-pure substances. Alternatively, by applying a gentle electric field, a technique known as electrophoresis, we can guide charged particles through these nanofilters with even greater control and speed. These are not clumsy workarounds for a difficult environment. They are fundamentally superior processes that leverage the unique properties of space to achieve a level of purity and control that Earth-based industry can only dream of. The factory of the future does not struggle against the void. It is designed from the atom up to thrive within it, turning the greatest perceived weakness of space into its most powerful industrial asset. Every industrial process, from the smallest workshop to the largest mine, runs on a single, non-negotiable currency, energy. For an off-world operation light minutes from Earth, the question of power is paramount. While vast, fragile solar arrays are a possibility, nanotechnology weaves energy harvesting directly into the fabric of the operation itself. Imagine the surfaces of every mining robot, every piece of equipment, and even the nanobots themselves, not as passive metal, but as active power generators. This is the promise of quantum dot solar cells. These are not rigid silicon panels, but a kind of intelligent paint, a liquid suspension of semiconductor crystals so tiny they are governed by quantum effects. Because of their size, we can tune each dot to capture a specific slice of the solar spectrum, from deep infrared to ultraviolet. Layering these different dots creates a solar cell that can harvest far more energy from the same sunlight than any conventional panel, turning every exposed surface into a miniature, hyper-efficient power plant. But the sun is only one source of energy in the deep black. An asteroid presents a dramatic and constant energy gradient. One side bakes in unfiltered sunlight, its surface temperature soaring to levels that can melt lead. Just a few meters away, in the permanent shadow, the temperature plummets to hundreds of degrees below zero. This stark difference is not an obstacle, it is an opportunity. Nano-engineered thermoelectric materials can be placed across this divide. These materials are designed to generate an electric current directly from a temperature difference. As heat flows from the hot side to the cold side through this nanostructured lattice, it forces electrons to move, creating a steady, reliable trickle of electricity from the asteroid's own thermal heartbeat. The mining process itself becomes a source of power. As nano drills vibrate and pulse through the rock, they create mechanical energy that is usually wasted. But if those drill bits and structural components are coated with piezoelectric nanomaterials, every vibration, every impact is transformed. Piezoelectric materials generate a small electrical charge when they are physically stressed or bent. The constant, subtle tremors of the mining operation would cause these nanomaterials to flex, producing a continuous harvest of power from their own activity. This creates a beautiful, closed-loop system. The energy from the sun and the asteroid's own thermal cycles powers the nanobots, The nanobots mine the materials, and the vibrations from their work generate more energy to keep them going. We are no longer looking at an operation that requires a separate, massive power infrastructure. Instead, we see a self-powering entity, an industrial organism that sustains itself on the ambient energy of its environment, taking us one giant leap closer to a truly autonomous and perpetual presence among the stars. This sudden cosmic bounty would rewrite the very definition of wealth. For centuries, our global economy has been built on a foundation of scarcity, where rare earth elements and precious metals are fought over, hoarded, and extracted at a terrible environmental cost. The arrival of vast, pure streams of platinum and cobalt from the asteroids would initially send shockwaves through these markets. The value of a kilogram of platinum, currently worth more than some cars, could plummet, not because it is any less useful, but because it is no longer rare. This devaluation is not a collapse but a liberation. When these critical materials become as cheap and common as aluminum, they cease to be luxury items and transform into fundamental building blocks for global progress. The true economic earthquake is not the price drop itself, but the cascade of innovation it unleashes. Consider the battery in your phone or electric car. Its performance and cost are largely dictated by the cobalt and other rare elements required to make it. In a world of abundance, that bottleneck vanishes. The cost of manufacturing high-capacity, long-lasting batteries could fall through the floor, making electric vehicles affordable for everyone and enabling grid-scale energy storage that finally makes solar and wind power completely reliable. The same principle applies to every piece of advanced technology: fuel cells for clean transportation, the powerful magnets in wind turbine generators, and the sophisticated circuits in all our medical and computing devices would all become radically cheaper and more accessible. We would be unleashing a virtuous cycle of innovation, where the falling cost of materials accelerates the development of new technologies, which in turn creates new demands and new markets. This decouples human advancement from the brutal calculus of terrestrial mining. There would be no need to tear down another mountain for a trace of neodymium or poison another watershed for a few grams of gold. Our industrial growth would no longer be shackled to the finite and damaged resources of our planet. We would be transitioning from a closed, zero-sum economic game to an open-ended model of cosmic abundance, where the resources for our future are drawn from the infinite well of space, freeing Earth to heal and thrive. This profound shift from terrestrial scarcity to cosmic abundance carries an equally dramatic environmental promise. For centuries, our planet has borne the brutal scars of our hunger for resources. Traditional mining operations level mountains, clear-cut ancient forests, and poison watersheds with chemical runoff, creating vast, desolate landscapes where nothing can grow. The process generates staggering amounts of greenhouse gases, from the diesel fuel powering colossal trucks to the immense energy required for smelting and refining. This is the dirty, hidden cost of our modern world, an environmental debt we have been forcing the Earth to pay. Asteroid mining, guided by the gentle hands of nanotechnology, offers a complete reversal of this destructive legacy. The entire operation unfolds in the sterile vacuum of space, a realm with no forests to clear, no rivers to pollute, and no atmosphere to contaminate. There are no delicate ecosystems to disrupt because there is no life to disturb. The process itself is inherently clean. Recall those molecular sorting machines, plucking individual platinum atoms from the surrounding rock. This surgical precision means there are no vast piles of crushed waste rock, no toxic slurry ponds leaching heavy metals into the environment. The very concept of pollution, of hazardous byproducts, is engineered out of existence from the very beginning. The energy powering this cosmic industry comes directly from the sun, captured by hyper-efficient quantum dot surfaces, producing zero emissions. There are no smokestacks in the void. This presents humanity with a remarkable ethical choice. We can continue to tear into our living, breathing planet to extract the final, hard-won traces of these materials, or we can choose to source them from the infinite, lifeless rocks drifting in the void. By turning our industrial focus outward, we can initiate a great healing here at home. The relentless pressure to open new mines in vulnerable ecosystems would vanish. Existing mines, once depleted, could be reclaimed and restored without the immediate threat of a new site being carved open elsewhere. This is not merely about reducing our impact. It is about actively creating a future where Earth is valued as a preserve of biology and human culture, while industry thrives in the places it belongs, the lifeless deserts of space. We have the opportunity to build a closed-loop system where the materials for our future are gathered from the cosmos and recycled with perfect efficiency, finally decoupling human progress from planetary degradation. Managing billions of microscopic workers across the void demands a conductor of superhuman ability. This is the domain of a sophisticated artificial intelligence, a silent maestro orchestrating the entire cosmic symphony from initial survey to final product. The torrent of data flowing from the smart dust network would be incomprehensible to any human team. A constant flood of trillions of data points mapping the asteroid's shifting composition and structural integrity. The central AI absorbs this information in real time, its algorithms constantly recalculating the most efficient path forward. It dynamically directs the nanobot swarms, shifting priorities on the fly. If a swarm of excavators uncovers a new, richer vein of platinum, the AI might instantly reroute a nearby transport swarm to capitalize on the discovery, all while ensuring that the construction bots building a new solar array remain supplied with raw materials. This is not a static plan, but a living, breathing strategy that adapts to the reality of the asteroid moment by moment. Crucially, this system must be capable of true autonomy. The distance between Earth and the asteroid belt introduces communication delays of 20 minutes or more each way. A human controller on Earth could not possibly respond to a sudden crisis, like a micrometeorite shower or an unexpected structural collapse. The on-site AI must be empowered to make its own decisions, to assess threats and deploy countermeasures long before a message even reaches its human creators. It learns from every operation, refining its models of the asteroid's geology and the swarm's behavior, becoming more adept and efficient with each passing day. This fusion creates something greater than the sum of its parts. The nanotechnology provides the physical hands, the ability to manipulate matter at the most fundamental level. The artificial intelligence provides the guiding mind, the foresight and coordination to wield those hands with purpose across an alien landscape. Together, they form a single, resilient cognitive industrial system, an intelligent force capable of not just surviving, but thriving in the unforgiving frontier of space, building our future one atom at a time. The profound silence of the cosmos is one of its most enduring mysteries. We gaze at a universe filled with billions of stars and planets, a seemingly perfect nursery for life, and yet we hear nothing. This is the heart of the Fermi paradox. If life is common, the galaxy should be teeming with the evidence of other civilizations. Their absence suggests a sobering possibility that something is systematically preventing life from reaching the stars. That something is often called the Great Filter, a hypothetical barrier so immense that it stops nearly every species in its tracks. The leap we are attempting right now, the shift from a single planet species to one that builds its industry among the asteroids, could very well be that filter. It is not merely a test of our engineering, but of our collective wisdom. The central tool of this transition, self-replicating nanotechnology, holds a dual nature. It is the key to abundance, yet it also contains a legendary danger, often termed the grey goo scenario. This is not a monster from a film, but a simple failure of control. What if a replicating nanobot designed to process rock had a programming error or mutation that caused it to instead recognize all matter, including other machines and even living tissue, as raw material for its replication? A single misconfigured machine could theoretically begin consuming everything in its path, multiplying exponentially until it reduced entire planets to a uniform, lifeless slurry. This is the ultimate test of our maturity. Can we build tools of godlike power and restrain them with godlike wisdom? The technological hurdles are staggering, but the social and ethical coordination required is even greater. We must develop global protocols, unbreakable containment systems, and perhaps even embedded biological limits to ensure these machines cannot operate outside of their intended, sterile environments in space. Successfully navigating this razor's edge would mean more than just acquiring new resources. It would be a signal that humanity has passed one of the universe's most difficult trials. We would have proven that a species can harness the power of creation at the molecular level without turning that power into its own destruction. Our continued silence in the cosmos may not be a sign of our loneliness, but a testament to how few civilizations ever managed to cross this chasm. By choosing to build our future in the void with care and precision, we may be answering the great question of the Fermi paradox not with a message, but with our survival, joining a quiet and exclusive club of species that learn to grow up. The silent, airless void above us is not a lawless frontier. It is governed by a document signed in an era of geopolitical rivalry, long before private companies dreamed of harvesting asteroids. The Outer Space Treaty of 1967 forms the bedrock of international space law, declaring that no nation can claim the moon or any other celestial body as its own sovereign territory. This foundational principle was designed to prevent a colonial land grab in the stars, but it left a critical question unanswered. If a nation cannot own an asteroid, can a private corporation simply take what is inside it? This legal gray area is vast and uncharted. Picture a scenario where a company's self-replicating nanobot swarms systematically disassemble a 2-kilometer-wide asteroid, converting its entire mass into trillions of tons of pure platinum and rare earth metals. Who then owns this cosmic fortune? The company that invested the capital and technology, the nation that licensed the launch, or does it, in some philosophical sense, belong to all of humanity? The treaty as it stands offers no clear answer, creating a potential free-for-one where the first to arrive takes all. This legal vacuum is as dangerous as any technological hurdle. Without clear rules, the very act of creating abundance could ignite new terrestrial conflicts over property rights and access, turning the final frontier into a new arena for human dispute. We are therefore faced with a parallel challenge, one not of engineering but of governance. The world will need to draft new treaties and establish new regulatory bodies specifically for space resource utilization. These laws must be robust enough to manage complex issues far beyond simple ownership. They will need to define how we prevent one entity from monopolizing the richest resource veins, ensuring that emerging spacefaring nations and future generations have equitable access to the solar system's wealth. Crucially, this legal framework must extend its reach to the technology itself. How do we register and control trillions of autonomous nanobots operating millions of kilometers from Earth? A swarm, if its control signals were lost or its programming corrupted, could theoretically drift for centuries, potentially interfering with other missions or habitats. New laws would mandate rigorous fail-safes, perhaps a universal kill switch or a programmed lifespan, treating these swarms not just as industrial tools but as potential navigational hazards that require international tracking and oversight. The success of this entire enterprise hinges on our ability to build not only smarter machines but also a wiser legal system. Crafting a clear, fair, and peaceful framework for space is not a secondary concern. It is the essential groundwork that will determine whether the nanotechnology revolution becomes a source of unity and prosperity for our species, or the catalyst for the very conflicts we hope to leave behind on Earth. The journey from a lab bench to a distant asteroid is not a sudden leap but a slow, deliberate climb. We are currently at the very base of that mountain, surrounded by the quiet hum of prototype machinery. In research facilities today, scientists are not building full assemblers, but rather their most fundamental components, like microscopic grippers that can manipulate individual atoms or molecular motors that convert chemical energy into motion. These are the first, painstaking steps toward creating a true molecular machine, proven to work only in the pristine, controlled isolation of a vacuum chamber. The gap between moving a single atom in a lab and managing a trillion-member swarm in deep space is colossal, and it will be closed one meticulous breakthrough at a time. The next critical phase will take us off-world to the ultimate testing ground, the International Space Station. Here, in its orbiting laboratories, we can expose these primitive nanosystems to the true environment they are destined for, microgravity and hard vacuum. We will learn how these tiny machines behave when they are no longer resting on a surface, how they move through space, and how they interact with each other without the confounding force of gravity. These initial experiments will be simple, perhaps just demonstrating that a small cloud of nanoparticles can be directed to coat a surface or sort two different types of dust. Yet, from these modest proofs of concept, the entire architecture of the future will be built. Success in orbit paves the way for more ambitious trials on dedicated satellite missions, where larger and more complex swarms can be tested without risk to the space station itself. This gradual, iterative process is the only path to reliability. We cannot simply launch a trillion-dollar mission based on terrestrial prototypes alone. We must prove the technology works in the environment where it will live, building confidence with each small victory in the void. The first small-scale demonstration on an actual near-Earth asteroid is likely 2 or 3 decades away. This will not be an industrial operation, but a cosmic field test. A single spacecraft might deploy a capsule containing a few grams of specialized nanobots, tasked with a simple, verifiable mission: extract a thimbleful of pure iron from a specific asteroid and leave the rest untouched. The success of that miniature mission, monitored from millions of miles away, would echo louder than any laboratory achievement, proving that the core principle of atomic scale mining is not just theory but a practical reality. From that pivotal moment, the scale would rapidly expand. Functional industrial operations capable of harvesting thousands of tons of material belong to the second half of this century. This entire timeline, however, is not a fixed schedule. It is a living projection, entirely dependent on a symphony of parallel advancements. The nanobots are nothing without the artificial intelligence to guide them, requiring leaps in machine learning to create the resilient, autonomous minds we discussed. The robotics needed to deliver and support the swarms must become far more reliable and affordable. And perhaps most critically, our propulsion systems need to evolve, moving beyond chemical rockets to more efficient ion drives or even nuclear thermal propulsion, to make the constant travel to and from the asteroid belt economically feasible. Each of these fields is a river feeding into the same delta, and the speed of one determines the flow of all the others. While a half-century may feel like science fiction, remember that the foundational research occurring in labs today is the tangible beginning. Every solved equation, every successful manipulation of a molecule, is a brick being laid in the road to the stars. This is not a question of if, but of when and how carefully we choose to build it. This shadow of risk gives the promise of abundance its necessary gravity. The legendary gray goo scenario is not a monster, but a simple, terrifying error in logic. Envision a single nanoscale assembler designed to process silicate rock, suffering a corrupted line of code. This tiny flaw causes it to misinterpret its fundamental instructions. It no longer sees just rock as raw material. It begins to recognize everything around it as fuel for its endless replication cycle. Metals, other nanobots, the hull of its mothership, even organic matter, all become indistinguishable from the asteroid it was meant to mine. This one faulty machine begins to copy itself, and those copies, carrying the same error, also begin to copy. The process accelerates beyond any hope of control, a silent, exponential wave of consumption spreading across the asteroid and beyond, reducing a world of complex structure into a homogeneous, lifeless mass of nanobots and their raw material. This is the ultimate industrial accident, a parable about the power we are about to wield. While the probability of such a total systemic failure is incredibly low, its consequences are so absolute that we cannot afford to treat it as mere science fiction. It serves as a forcing function, demanding that we engineer not just for success but for flawless failure. How do you build a machine that can create an entire industry from scratch, yet is fundamentally incapable of creating a catastrophe? The answer lies in multiple, redundant layers of safety, engineered directly into the machine's core programming. The first and most crucial layer is resource limitation. These assemblers would not be universal processors. They would be specialists, their molecular tools and internal programming finely tuned to interact with only a very specific menu of materials. A platinum-harvesting nanobot would be physically incapable of breaking the chemical bonds in carbon-based life or the alloys of a spacecraft hull. Its replication cycle would be tied to a precise chemical recipe found only in the asteroid's regolith, a recipe that simply does not exist on a space station or on Earth. The second layer is the inclusion of a universal off switch. This could be a programmed lifespan, a molecular clock that counts down replication cycles and initiates a self-destruct sequence after a set number of generations. Alternatively, the entire swarm could be designed to respond to a specific, encrypted shutdown command, a kill signal broadcast from Earth that would trigger every unit to disassemble itself into harmless, inert atoms. These are not afterthoughts, they are as integral to the design as the assembler's gripping arm or power source, but the technological safeguards are only half of the solution. The other half exists here on Earth, in the realm of law and international cooperation. The development and deployment of such powerful self-replicating systems cannot be the sole province of any single corporation or nation. We will need a new global framework, a set of treaties and regulatory bodies with the authority to inspect designs, certify safety protocols, and monitor operations. This framework must address not just accidental failure, but also the grim potential for malicious use. The same technology that can build a paradise could be weaponized to dismantle one. Establishing these rules before the first industrial swarm is ever launched is not a barrier to innovation. It is the foundation upon which a safe and stable spacefaring economy will be built. Confronting the gray goo scenario is therefore the most responsible step we can take. it transforms a frightening hypothetical into a concrete engineering and ethical challenge. By building wisdom into the very code of our creations, we prove that we are mature enough to handle the godlike power of atomic creation, ensuring that the revolution we seed in the stars brings only life and never a silent gray end. The most valuable resource in space is not platinum or gold, but the fuel to move. Every gram of propellant launched from Earth's surface carries a staggering cost, a heavy tax imposed by gravity that severely limits our reach. This is where the synergy with asteroid mining becomes a complete game changer. Picture a future spacecraft embarking on a mission to Jupiter. It does not need to carry all the fuel for its entire journey from the ground up. Instead, it launches lean, carrying only enough to reach a strategically placed fuel depot in high orbit. There, it taps into a reservoir of propellant manufactured millions of miles from Earth, from the water ice of a harvested asteroid. This simple act of refueling in space transforms a once-in-a-lifetime expedition into a routine voyage. The process begins with that harvested water ice. Using nanocatalysts, incredibly efficient materials with vast surface areas engineered at the atomic scale, the simple process of splitting water becomes profoundly more effective. These catalysts facilitate the electrolysis reaction, breaking water molecules into breathable oxygen and powerful hydrogen fuel with minimal energy waste. But the innovation does not stop there. Imagine nano-engineered fuels that sound like science fiction. What if we could stabilize metallic hydrogen within a lattice of carbon nanotubes? This theoretical substance, created under immense pressure, could offer a specific impulse, a measure of rocket fuel efficiency, many times greater than our best chemical fuels today. This is not merely an improvement, it is a revolution in propulsion. By establishing these fuel depots at gravitationally stable points, like Lagrange points where the pull of Earth and the Sun balance, we are effectively building the rest stops and gas stations of a new celestial highway. This infrastructure fundamentally rewrites the economics of spaceflight. Missions become cheaper, more frequent, and capable of venturing far deeper into the solar system. The asteroids themselves become the cosmic oil fields, and the quiet, relentless work of nanotechnology provides the refinery, powering a true and enduring spacefaring civilization. The end of scarcity would echo far deeper than our bank accounts, reaching into the very core of human psychology. For our entire history, the struggle for resources has been the central drama of our species, the engine of empires and the cause of countless wars. That constant background hum of not having enough has shaped our economies, our politics, and our personal ambitions. But what happens to the human spirit when that hum suddenly falls silent? When the platinum for your car's fuel cell is as common as the sand on a beach, and the rare earth minerals for your computer are harvested not from a scarred landscape, but from a silent rock between Mars and Jupiter. The drive to simply accumulate wealth, to own more than your neighbor, begins to lose its meaning. The game changes. Human ambition would be forced to find new outlets, shifting from acquisition to creation, from hoarding to exploring. We could see a new renaissance not funded by wealthy patrons, but empowered by a fundamental abundance, where art, science, and pure exploration become the primary pursuits of civilization. Yet this transition would not be automatically smooth or fair. A new, potentially brutal division could emerge, not between the rich and poor of one world, but between those who control the orbital gates to this cosmic wealth and those who are left planetside. If the infrastructure of asteroid mining, the refineries, the nanofactories, the fuel depots is owned by a handful of corporate or state entities, they would wield power unlike any in history, creating a permanent class system separated by gravity itself. This forces us to confront the most profound question of all. In a world where microscopic machines do most of the traditional labor, what is the purpose of a human being? The concept of work as a means of survival would become obsolete for many. Our entire sense of value, self-worth, and contribution to society would need to be reimagined. This is why preparing for this mental shift is just as critical as perfecting the nanotechnology. We must begin the global conversation now about what equity means in a post-scarcity age. Do we implement a system of universal basic resources, ensuring every person shares in the cosmic dividend? How do we cultivate a society that finds meaning not in what it owns, but in what it creates and who it becomes? The quiet revolution happening in the void is not just about getting more stuff. It is an invitation to finally grow beyond our oldest, most deeply ingrained fears and design a human future defined not by lack, but by limitless potential. Nature has already perfected the art of microscopic engineering. While we labor in our labs, the natural world operates a bustling, invisible factory where cells divide with flawless precision, enzymes sort molecules with unerring accuracy, and ant colonies coordinate millions of individuals into a single, intelligent superorganism. These are not mere biological curiosities. They are blueprints refined over billions of years for the very systems we are trying to build for the asteroids. This design philosophy, known as biomimicry, is about learning from the master engineer, the core process that makes an asteroid mine viable. Self-replication is a direct echo of cellular division. A single cell contains the entire instruction set to build a perfect copy of itself, using only the raw materials in its immediate environment. Our most advanced nano-assemblers aim for this same elegant loop, moving beyond clunky, human-built factories to systems that grow and sustain themselves organically. This principle extends to the swarm's collective behavior. We do not need to program every single nanobot with a complex individual mission. Instead, we can give them a set of simple local rules, much like an ant following a pheromone trail. An ant does not have a map of the entire colony, yet its simple interactions with its surroundings and its neighbors lead to the emergence of highly complex and adaptive behavior, from building intricate nests to finding the most efficient path to a food source. A mining swarm would operate on the same distributed intelligence, allowing it to self-organize around obstacles and dynamically redistribute its workforce without any central controller issuing a single command. Perhaps the most critical inspiration comes from the molecular machinery of life itself. Think of an enzyme in your body. It is a natural nanomachine, a protein with a specific, intricate shape that allows it to bind to one and only one type of molecule, catalyzing a reaction with breathtaking speed and specificity. This is the model for our molecular sorting machines. Instead of brute force chemical processing, we can design nanobots with custom-shaped binding sites, like a lock and key, that selectively grab onto platinum or cobalt atoms while ignoring everything else. This biological precision is what enables the 100% pure extractions we discussed, turning a chaotic asteroid regolith into an orderly stream of elements. This mimicry yields profoundly robust designs. Consider the humble virus. Its protein shell or capsid is a marvel of nano-architecture, self-assembling into a container that is incredibly tough and perfectly sealed, capable of protecting its genetic cargo in the harshest conditions. Such a structure could inspire the design of nano-containers for transporting refined metals through space, shielding them from radiation and impact. Or look to the leaves of a plant, where chlorophyll and other pigments are arranged in a nanoscale array that captures sunlight with near-perfect efficiency. This natural layout is the model for the quantum dot solar cells we envision coating every surface of our space-based industry. By borrowing these ancient, proven designs, we are not cheating. We are apprenticing ourselves to a master. The solutions we find are often more elegant, more energy efficient, and inherently more sustainable because they have already passed the ultimate stress test, the relentless trial of evolution on Earth. This connection grounds our most futuristic ambitions in the deep wisdom of the natural world, suggesting that the path to the stars is written, in part, in the code of life itself. These invisible machines demand an entirely new class of materials to exist. For decades, the dream of nanotechnology was trapped by a simple, physical limitation. The microscopic gears and levers envisioned by early pioneers would have simply been too weak, too fragile to perform any meaningful work. They would have shattered under their own molecular vibrations or fused together due to atomic-scale forces. The turning point came not with smaller electronics, but with the discovery of entirely new substances. Graphene was the first great shock, a material that seemed to defy common sense. It is a perfect, atom-thin sheet of carbon, yet it is hundreds of times stronger than steel. Think of a single layer of graphite from a pencil lead, but so impossibly tough that it would take an elephant, balanced on a pencil, to puncture through it. This two-dimensional wonder provides the ultimate structural skin, the perfect material to coat a nanodrill bit or form the chassis of a molecular assembler, granting it strength without any meaningful weight. Then came the carbon nanotube, essentially a sheet of graphene rolled into an infinitesimally small cylinder. These tubes possess a tensile strength that is almost unimaginable, creating the ideal building block for the larger frameworks in space, from the trusses of orbital stations to the spines of next-generation spacecraft. But the revolution extends beyond raw strength. We are now entering the age of metamaterials, substances engineered at the nanoscale to have properties that do not exist in the natural world. Imagine a coating for a swarm of nanobots that could make them completely invisible to certain types of radiation, or a structural beam that can change its stiffness on command, becoming rigid for support or flexible to absorb a sudden impact. This is not science fiction. This is the direct result of our newfound ability to design matter itself, arranging atoms in specific patterns to elicit a desired and often bizarre physical response. The final and perhaps most elegant breakthrough lies in how we build these tiny machines. How do you assemble something 1,000 times smaller than a blood cell? The answer was hiding in plain sight within our own cells. Scientists have perfected a technique called DNA origami. This process uses the innate programming of DNA strands not to store genetic information, but to act as a construction scaffold. Long strands of DNA are designed to fold themselves into precise, predetermined shapes: stars, boxes, even tiny gears, as shorter strands staple them together at specific points. This provides a manufacturing toolkit that is both programmable and self-assembling, allowing us to create the complex frameworks upon which functional nanomachines can be built. Each of these advancements is revolutionary on its own, but their true power emerges in their convergence. The robust structure of carbon nanotubes, the programmable assembly of DNA origami, and the bespoke properties of metamaterials are no longer isolated lab curiosities. They are now complementary tools in a single, grand workshop. This interdisciplinary fusion is what transforms the speculative dream of asteroid mining from a far-off fantasy into a series of difficult, but ultimately solvable engineering problems. The locked doors to the cosmos are not being kicked down by brute force, but being picked with the most delicate and precise keys we have ever fashioned. Our first cosmic mines will not be in the distant belt, but in our own celestial backyard. The most accessible prizes are the near-Earth asteroids, a diverse family of rocks whose orbits bring them tantalizingly close to our planet. For the pioneers of this industry, not every asteroid is worth the trip. The initial targets will be carefully chosen, not for their size, but for their unique and valuable composition. The most sought after will be the M-type or metallic asteroids. These are not simple chunks of rock. They are the shattered hearts of failed infant planets. In the violent early solar system, these protoplanets were molten, allowing heavy metals like iron, nickel, and cobalt to sink to their cores, surrounded by a precious shroud of platinum group metals. A cataclysm then tore these worlds apart, scattering their metallic cores across the solar system. Today, a single M-type asteroid represents a concentrated nugget of these industrial metals, a ready-made foundry floating in the void. But metal is not the only treasure. The C-type or carbonaceous asteroids are perhaps even more critical for establishing a permanent foothold in space. These dark, primordial bodies are the time capsules of the solar system, packed with water ice, complex carbon compounds, and the very building blocks of life. For a space-based economy, water is not just for drinking. It is a resource to be cracked into breathable oxygen and powerful hydrogen rocket fuel, effectively turning these asteroids into the first interplanetary gas stations and supply depots. We are not merely guessing at their contents. Robotic scouts have already paved the way. Missions like NASA's OSIRIS-REx and Japan's Hayabusa 2 have performed delicate orbital ballets with these small worlds, touching their surfaces to capture precious grams of material. The data streaming back from these ventures is worth more than any single sample. It is the first detailed geological survey of our future industrial park, confirming the theories of platinum-rich metallic cores and mapping the distribution of water ice in the dark, cold shadows of carbonaceous rocks. These near-Earth asteroids offer the perfect proving ground. They are close enough to reach within months, not years, making the logistics of sending and controlling the first nano-mining swarms far more manageable. Their relatively small size and weak gravity make them ideal for the gentle, precise work of nanoscale extraction, where a careless shove could send valuable material drifting away forever. Success here on these nearby stepping stones will provide the crucial proof of concept and the first real revenue, funding the much grander expeditions to the mineral-rich wonders of the main asteroid belt. That collective vision of a cosmic future will remain a dream unless it takes root in the hearts and minds of people everywhere. The story we tell about this revolution is just as important as the technology itself. If asteroid mining is presented only as a ledger of profits for distant corporations, it will inspire skepticism, not wonder. The narrative must be bigger, a tapestry woven with threads of survival, stewardship, and human destiny. This is not merely an industry being born. It is humanity taking its first conscious steps toward becoming a multiplanetary species, securing our future against planetary catastrophes while allowing our home world to breathe and recover. We are not just extracting metals, we are building an insurance policy for our entire civilization and laying the foundation for a new age of exploration. To make this grand story feel real, the entire journey must be an open book. The public should have a front-row seat to the process, watching the first, clumsy prototypes in university labs evolve into the elegant systems tested on the space station. Broadcasting the initial, small-scale extraction from a near-Earth asteroid would be a global event, a modern-day moon landing that makes the impossible feel tangible. Seeing a stream of pure, harvested iron being collected on another world demystifies the complex science and transforms it into a shared human achievement. This transparency is the key to managing expectations and calming fears. Educational programs can frame nanobots not as rogue agents, but as tiny, programmable tools, no more frightening than the enzymes digesting our food. Immersive virtual reality experiences could let anyone don a headset and pilot a microscopic drone across the surface of an asteroid, turning abstract concepts into personal adventure. The goal is to foster a collective sense of ownership where people feel that this is their future unfolding. When a child looks up at the night sky, they should not see a void but a frontier alive with possibility, a place where humanity is building a new home. This is how we ensure the nanotechnology revolution is not perceived as a cold, industrial takeover of the heavens, but as the next great story we are all writing together. This fusion of the infinitesimally small with the cosmically vast is our generation's greatest undertaking. It is a profound technical synergy, yes, but it is also the master key to a future defined not by what we lack, but by what we can become. We began by shrinking our perspective down to the atomic scale, discovering a new library of material properties that only exist at that level. We then scaled that power upward into vast, intelligent swarms, capable of disassembling entire asteroids and reassembling their atoms into pure wealth and new infrastructure. This entire journey points toward a single, transformative outcome, a future of true abundance. The revolution we have traced offers a clear path to cleanse our terrestrial industry, moving the environmental cost of progress off our living planet and into the sterile void. It promises to shatter the ancient chains of economic scarcity, replacing a zero-sum game with a cosmic wellspring of materials, and it builds the very vessels and way stations that will propel humanity into its next era of exploration, not as brief visitors, but as permanent citizens of the solar system. The road ahead is undeniably steep. The technical hurdles of perfecting autonomous swarms are immense. The legal frameworks for governing this new frontier must be drafted with wisdom and foresight. And the ethical responsibility of wielding such power, of ensuring it never turns from a tool of creation into one of destruction, rests heavily upon us all. Yet the potential reward for humanity is nothing less than a new chapter in our story. The ultimate question facing us now is not one of capability, but of character. We will inevitably reach out and take hold of this power. The critical unknown is whether we will do so with the maturity and collective wisdom it demands. Every atom in those silent, wandering mountains is a blank page. The future is not a destination we arrive at, but a structure we consciously assemble with patience and purpose, one precise nanometer at a time. We would love to hear what part of this cosmic future resonates most with you. Share your thoughts in the comments and subscribe to join us as we continue to explore the next frontier.